Hi everyone. In this video, we're going to continue on again with more discussion about the normal distribution, and we're going to get to our last two distributions, which are exponential and gamma distributions. So another important part, or another important fact about the normal distribution is that we can, given a mean and standard deviation, we can predict with some certainty, or we know because it's a normal distribution, that a certain percent of the data lies in between one standard deviation or two standard deviations from the mean, or three. Okay. In fact, you've seen this a lot actually throughout the book in homework questions where I try to skip over them. They often are interested in calculating the probability that the point is within two standard deviations of the mean. Okay, and this is why they keep saying that in those things there. It's because it's actually an important idea that sort of plays out later on. And so the normal distribution has this property to it. 68% of the distribution is going to lie in between plus or minus one standard deviation of the mean. Okay, so you take the mean plus a standard deviation and mean minus a standard deviation. That creates an interval, and the percent between those intervals is 68. Okay, when you change from 1 to 2, it's 95, and then when you change to 3, it's 99.7. Now that seems cool, great, but what sort of is it use? What's the use? And one thing is that it helps us detect if an observation is far away from the rest of the data from a normal distribution, and that has a name, and that name is an outlier. Okay, and we're going to talk about that later. But it turns out that outliers play an important role in statistics. And so it's sort of important for us to be able to detect outliers. Certainly, if you fall more than 3 standard deviations away from the mean, you are in not the 99.7% that lies in, you're in the 0.3% that lies with, outside of those. And so you're pretty rare if you do that. Hence, you are not standard, meaning you're an outlier. That's not all we'll use it for. In fact, a lot of what we do, again, I've been saying this a lot, but a lot of what we do has this empirical rule kind of thought process behind it. And so I will definitely mention it again. Now, there is, for the empirical rule, this applies only to normal distributions. Okay, so it implies in the specific definition of it, it might only apply to symmetric bell-shaped distributions, and it turns out that the only one that really matches that is the normal, and maybe one other distribution that we'll talk about later on. But it is only for normal distributions. There is another rule that we're going to talk about a little bit later called Chebyshev's rule, or Chebyshev's inequality. And it is less powerful, meaning it can't tell us with as great of certainty what is going to happen, in a sense, here, like the normal distribution is, but it applies to any distribution, not just the normal. So it's something that we'll learn later on, but I just thought I'd mention here. Now, as a visualization, no, never mind, no visualization. One last sort of part about the normal distribution here is that it turns out that it's not only a good model for data that is said to be normal, It's also a good model for some discrete populations. And so something that we might use the binomial distribution for, or the Poisson distribution for, or negative binomial, so on and so forth. It turns, not all of them, but some of them actually start to look like a normal distribution after you get enough data in. After you get a sample of size large enough, it's going to look symmetric and bell-shaped. And so that is certainly true, and it used to be a big thing called the normal approximation to the binomial distribution. And so there's a fact that says if there are enough successes and failures in the sample, and specifically they even define some rules here that say n times p and n times 1 minus p have to be greater than or equal to 10. If that's true, then they say you can approximate that binomial distribution with a normal one. And so if you'll remember, the normal has a mean, the binomial mean is n times p, and the binomial standard deviation is the square root of n times p times 1 minus p. And so if you take those means and standard deviations, plug them or substitute them into the normal distribution, you get this, what I have written down. And this used to be a really big thing. And you might wonder why. I mean, if I can use a binomial distribution, why don't I get an exact answer? Why would I be interested in an approximate answer? And the answer to that question is people knew how to calculate probabilities easily with a normal distribution before they did with a binomial distribution. So if you remember, not so long ago, the tedious process of calculating a probability about a binomial distribution. You had to do the choose operator, which is not nice, not easy. And so it took you a little while to do that. And especially if you had a problem where there were, 200 observations, that's a lot of calculating to do. And so if you could approximate it well enough with the normal distribution, which has been around for a long, long time, and people knew how to do easy calculations with that, they're going to use the easy calculations over the tedious ones, even though, in a sense, the binomial is better than the normal because it is exactly what's happening, not just approximately. Still, easy calculations are better than hard ones. But with software like Minitab, it can do binomial calculations just as easy as normal ones. And so why am I using an approximate answer when the exact answer is now easily obtainable without having to do a lot of tedious calculations? So I said a lot there, but hopefully that made sense. This is true. Something that's true used to be a big deal, is now not so much of a big deal. But here's a visualization of how the binomial distribution can start to look like the normal distribution. So the histogram, which is the bars, are the binomial distribution, PDF, but instead of just single points, they put bars centered at each value. And the blue curve is the sort of overlaid normal distribution that has a mean of n times p and a standard deviation of square root of n times p times 1 minus p. And so you'll see that it actually fits very well. And thus, it could give you pretty much the right answer. So that's the normal distribution. Those are some facts that I'm not necessarily going to make you do a lot of problems on, but it's important to know. Now we get to the exponential distribution. And this is the first case really of of a continuous distribution that isn't symmetric. And I say this sort of nonchalantly, but I should make sure to not say it nonchalantly because we haven't really learned what symmetric is. Symmetric means that if I cut the graph of the PDF in the middle, down the middle, and I flip one side over onto the other, I'm going to see the exact same picture. Okay, so if I split it in half, fold one side over on the other, they look the same. We often like symmetric distributions for a number of reasons that we don't have to talk about here. The exponential distribution, and in fact the other distribution that we'll talk about called the gamma, which is a generalization of the exponential, are non-symmetric. And so it's important to mention that they aren't because it's just different to note that all are not symmetric. But here's the exponential distribution. It looks like this. So in the first blue box, it gives you the PDF. Okay, so it gives you the PDF. The exponential distribution has one parameter. It's what they call a scale parameter. The scale parameter has to be positive. Okay, so it has to be greater than 0, and x has to be non-negative. X is greater than or equal to 0. So it turns out that the exponential distribution is a lot like the Poisson distribution in that it looks at waiting times of an event, or the time. So the exponential distribution actually looks at time between events. The Poisson distribution looks at the number of events that happen over a given time or space interval. Exponential distribution is kind of like that. And it has a fairly simple PDF, lambda times e to the negative lambda x. Okay. Below it has a CDF, which is easy enough to integrate the top to get the bottom in the way that we sort of talked about before. So there's the PDF and CDF. And the mean of the exponential distribution is lambda. 1 over lambda, and the variance is 1 over lambda squared. Okay. Great. So let's look at an example. Again, what you're usually going to do for these distribution questions is you're going to turn to Minitab. Okay, because why not? The article Probabilistic Fatigue Evaluations of Riveted Railway Bridges suggested that the exponential distribution with a mean value of 6 MP as a model for the distribution of stress range in certain bridge connections. Okay, great. So if the mean was 6, then the lambda parameter, since the mean is 1 over lambda, means that the lambda is 1/6. Okay, and so our scale parameter, which they call it, is 1/6. Great, and I want you to find the probability that it is at most 10. The stress range is 10, or it's between 5 and 10. So again, we're going to turn to quickly, and again, we're going to go to calculate probability distributions. For Mac users, I have to choose the kind of probability I want, and the first question was at most 10, and at most is less than or equal to, which is a cumulative probability. So I go to cumulative. Here I can choose from a bunch, and I'm going to choose exponential, which is up here, exponential. It gives you a couple of different options here, or rather, there's this threshold and scale thing. Always leave the threshold for us at 0. And so the scale, scale equals mean if threshold is 0. That's not what we want. Maybe the threshold is 1. 0.1667. I didn't look at this as much as I should have before I started making this video, and so we're sort of flying by the seat of our pants here. 10. Okay, I'm not exactly sure what this threshold is, so what we're going to do is we're going to go cumulative probability with a threshold of 0. Okay, so if threshold is 0, then the scale is equal to the mean, not 1 over. So we're going to say scale is 6, and then input 10 here. Okay. So again, I don't know if you remember way back, but the negative binomial distribution had 2 different parameterizations, meaning that it sort of meaning that one of them was counting the number of failures until a certain success, and and another one was counting the number of total trials until the rth success or the certain success. It's the same sort of thing here. Some parameterizations flip that scale. Instead of 1 over lambda, they make it lambda. And so that changes the PDF a little bit. And so actually that's what we're going to go with here, since that's how Minitab seems to like it. So our scale is the mean, which is 6. We're looking for at most 10, so I click OK. And the answer to part 1 is 0.811. Okay. And then the second part, the second question, is that between 5 and 10. Okay, between 5 and 10. So down here I'm going to put 10 and 5. For continuous distributions, it doesn't matter inclusive or exclusive, because there's no such thing. And so I am going to input a column of values, C1, exponential, 6 and 0 there. And so I click OK. And it gives me up here the 2 values, 0.811 minus, and so what I do is 0.811 minus 0.565. And if we just do that quickly here with a calculator, 0.811 minus 0.565 will store results in C2. It turns out that that difference is 0.246. Okay, and so then that would be the probability that exponential distribution, the probability that the random variable would be between 5 and 10. Okay, it's 0.246.